Good afternoon. Welcome to this presentation. We have a joint presentation together, July and me. The topic is about control of adaptation, and that's a way how you can make adaptation more context sensitive, which is in the literature a bit underrepresented, but we think that's a very important concept. And we show how you can do that and how you can apply it in a number of cases, which gives you interesting achievements in those applications. Some part of the work is work also done together with Reis Palwankar and Laila Famens, especially the first half that I will present. And the second part is the work that July and I did even just this year, but where we were able to find really interesting and important progress on the field of organizational learning. So the contents are as follows. We will discuss what mental models are, and we will show an overall cognitive architecture for them. We will show how self-modeling networks can be used to make it computational. And different types of context-sensitive control of adaptation will be shown, will be distinguished and related to the idea of self-modeling networks. But then a big part by July will be on how to apply such concepts to achieve something that was very challenging actually, but we were able to get to something at least now. The area of organizational learning, where you use individual mental models to get shared mental models for an organization, and where you also let individuals learn from shared mental models, like what is called feed-forward learning and feedback learning. And then the control of these forms of learning is a very important issue. So that shows that will illustrate the importance of this control issue. The first part of the talk will also be in this book, which will come out in 1 or 2 months this year. The second part is will be the content of another book that will come out halfway next year, the second half of next year. So mental models, they are things in your head, kind of small scale models, and then you can use them to try out in a simulated manner in your brain what can happen next, what can happen in your future when you do certain things. So it's a form of what-if simulation, you can say, and you can use it to make decisions what is the best option then, because you have found out what the possible consequences are. You have to learn them usually at some point in time, and then also to keep them, to not forget them. So that's also an important aspect of mental models. And if you use them, or by using them, you can just have a safer environment, a safer life, and especially when otherwise emergencies may be around the corner. So that's also an issue. Mental models are relational structures, and that means that you have a kind of working model in the brain which has a kind of similar structure as the world itself. So suppose in the world you have a causal relation from one world state to another world state, then in the brain you also have such a causal relation, but then from one mental model state to one other mental model state. So this, in the case in your brain, if you activate this one, you automatically will also activate that one. But like in the world, when this happens, then also that will happen. So that's a bit the idea of the small scale model in your brain. Well, that's an interesting topic. There is a lot of attention on that in the educational science literature, because it's thought that many learning processes make use of mental models, and then you learn them or you maintain them to not forget them, for example. Already Piaget was pointing at these types of structures. This is an example that illustrates Piaget, not from his time, but from this time. suppose you need something, then a mental model can be, okay, then you have to go to a shopping area. But suppose now that you need a specific thing, like a book, and yeah, then you do need something, but then you also need to have more relations in your mental model to find out that you have to go for a bookshop, for example. So this process is called assimilation in terms of Piaget. So you refine your model. It's not changing because this part is still there. And so that's how you make it more rich, more detailed in a certain way. But there is also an option of accommodation distinguished by Piaget. For example, during a pandemic like we have now, if you need a book, you will not go to a shopping area when that shopping area is closed, and then you will have to find another mental model, like go to a web shop. So that's, you need to accommodate, but accommodation is not always easy. For example, here you see somebody who has some difficulty to do accommodation. He still goes to the shopping area, and then he starts to complain that it is closed. So he really is a bit annoyed about that. This is also sometimes called the exploit-explore dilemma. So he just exploits the old structure and he doesn't want to explore new options. So that's an example to illustrate the difference between these options. So learning of mental models is a big topic in educational science literature. For example, you can learn by instruction, somebody tells you how to do things, or you can learn by trying it out yourself and to observe, or to observe other people, how they do it. So there are combinations of all these forms, and if in an actual learning process, you need also to control that. So you need certain, what is called metacognition, to control whether you want to listen to maybe a YouTube movie or a teacher, or whether you want to try things out yourself or to see other people doing things. So that's really a big topic in educational science, also quite informal and not formalized and practically not in computational manner modeled. So what we have now is that we can do model such things in a computational manner, in a formalized computational manner. So the first step in that is that we first have a cognitive architecture for mental models. So we have the use of it by internal simulation. We can have the learning, the adaptation of it, and we can have the control of them. So that's what you have then as 3 different levels, distinguished as a cognitive architecture structure. So this is then a kind of relational structure, and these relations are changed by adaptation, and then there is control over that. So how do we make that computational? Because a cognitive architecture is still a bit fake, fake type of concept. So then we will use the idea of a network model to make it computational. Well, the network-oriented modeling approach we use makes use of a number of characteristics of networks. So 3 main types of it. First, for the connectivity, we use the connections from one node to another state and their connection weights. We also explicitly specify the aggregation. If you have multiple connections to one state, it's not clear how you should combine their effect. So therefore we have an option to just specify that you can just take a sum function, logistic function, maximum or minimum function, any function you want to use. We have a library of at the moment 50 types of functions that you can just apply. And the third type of characteristic is the timing characteristic of a network, the speed factors by which the states, the nodes are also called states in this case, are changing, because the nodes have activation levels and therefore they have states per time point. And then the speed of changing is also can be specified for different nodes, different states separately, so that they don't need to be synchronous all the time. So if you don't have speed factors, you may have an implicit assumption that all of them are synchronous, which is for real applications usually not the case. So that we can specify that also. Behind everything, there is a canonical difference equation that's also in the software environment. So you use the combination function to combine the different impacts from different sides on a certain node y. You compare it to the y and you add a fraction of the difference to the y so that it changes in this direction. And that's your next value for the next time point. This is a very useful and very general purpose type of equation. It is actually equivalent with any dynamical system. I have a proof for that in another paper. So it's very general, but it turns out very useful because having that in the software, you don't need to do such procedural or even programming things. Now, networks can also be adaptive. Many networks are adaptive, and like we want to also discuss learning here, we should also consider adaptive networks. And that means there is at least part of the network structure characteristics change over time. Like you can have them in different forms. Connectivity can change over time. These are changing connection rates. Like if you have artificial neural networks, usually the focus is on changing their connection rates. That falls under this category. But you can also have changing combination functions. For example, if you change dynamically the functions used in artificial neural networks, then you fall under this category. Well, for example, you can have the excitability threshold taus that you often have in your formulas. Then you have aggregation adaptation. And you can have timing adaptation where you change your speed factors on the run. So these are the different categories of adaptation for a network, but you can have also mixed forms. Some of the connections are changing, some of the speed factors are changing. Many possibilities are there. So to model adaptive networks, there is often people make use of just programming code to program how they change. That's not what we do. We use a network-oriented way to address also adaptive networks. And that goes, in fact, it's based on this metaphor, a kind of picture-in-picture metaphor. Suppose you have a picture and there is part of the picture, there is a new picture there that represents in a certain way the overall picture as well. So this is a self-model for this picture as a whole. And this is another example. Then this picture here is a self-model for what is really there on the bigger picture. You can also have self-models in a novel, for example, that somebody is writing a novel within your novel, or in a movie. There is a movie they made up in some movie or a theater. There is a play within the play. So there are many cases in such areas that make use of self-models. But we use them for networks. And how can you do that? Well, that's not so difficult. You just add some extra network structure, a subnetwork with states that represent network characteristics. So you have additional nodes, but they mean and they are connected to certain network characteristics. For example, you can have a self-model for your connectivity, like the connection weights, for aggregation, for timing. This is an example of the three of them. You have three network characteristics, one connection weight, one excitability, one persistence factor, I can say here, and one speed factor. And then we want all of them adaptive. Then we add just a kind of states for them, nodes, new nodes in the network. They are called self-model states. And from that time on, this value represents that, and this value represents this, and so on. So if you change this value, it will be adaptive. And you can change it because in the network, you can have the normal dynamics. So this is what you normally do in dynamical systems. If you want to have an adaptive dynamical system, you introduce new variables for all the parameters that you want to have adaptive. But in this case, the special thing is that these variables, they are just network concepts. So that makes it special in this case. So you can, as the result of a self-modeling network, as a network itself again, you can repeat it. You can have an iterative application of the notion of self-modeling. And then you can have also a second order self-model states. So suppose this W is a first order self-model state for the omega. And then you can have like this, the learning speed, the eta, you can introduce a second order self-model state for that, or for the persistence factor for the learning, you can also add a second order self-model state for that. Very easy, it's just the same idea, you just build your networks. You design things by building networks. And for example, for Hebbian learning, you need to build networks, you also need the combination functions. And this is the combination function that's often used for Hebbian learning. You see, you just describe a declarative mathematical function. You don't need to do any work for the procedural way of processing it, for any algorithm to do it. That's just taken care of by the software environment, where we have this canonical difference equation in it, which is applied also to the self-model states. So that's the general idea of self-modeling network. So they can be very useful to model adaptive systems in a network-oriented manner, and also to get higher order adaptive systems, which is in the literature not so easily done and not so easily found. And no programming is needed, and it covers just complex dynamics, adaptive dynamics within network-oriented modeling. There is some inspiration from neuroscience about this. In neuroscience, the notion of plasticity is well known, that you can change synapses, for example, but also change intrinsic properties of the neurons over time, like a form of adaptation and learning. That's called plasticity. But you also have principles like adaptation accelerates with increasing stimulus exposure. And that's talking about adaptive speed of plasticity. So that's not the normal plasticity. That is what you call metaplasticity in the literature. And then you have also what is called the plasticity versus stability conundrum in that literature, which is a bit like the exploit-explore dilemma. The question is when you want to learn, what are the circumstances where you want to learn. Here in this case, you only want to learn when there is stimulus exposure, not in all these other cases. And so this gives you a context-sensitive adaptation control. So that's to solve these types of things, these conundrums or dilemmas. That's the solution in all these things is make a third level above the adaptation level and then make things context sensitive there and use that as control for your adaptation. And that it's really supported by this literature in neuroscience. So this is then the general structure of the cognitive architecture. Then we can make a self-modeling network out of it like this. Suppose this is a mental model that we have in the base level. We want to learn this connection. We have a W state for that. And the W, this is a first order self-model state. And then this is the second order self-model state, and also that one for the speed of the learning and for the persistence of the learning. So in that way, we make this cognitive architecture a computational model, a self-modeling network. So in this way, we can have a number of options. You can have adaptive connectivity characteristics and control over that. And for that control, you need something that you can call WW state. So you have connections that lead to your W states that are used for the learning. And these connections, you can change them over time, depending on the context. So that's one option. That's for the connectivity. We also have for the aggregation. So then you can have C states, and for the combination functions choice for your W, like the Hebbian learning function can be changed into another one. And for the persistence, like the persistence factor for the Hebbian learning, it can be changed by this control that you can use by the second order self-model states. And finally, also for the timing characteristics, you can do similar things. Then you have the HW states. So this framework gives you another number of possibilities that are distinguished. And we actually have used all of them in different applications, and also in this organizational learning case that will be discussed by July in a minute. So let's consider that. Computational modeling of multi-level organizational learning. The organizational learning itself in literature is usually described by pictures like this. There are individuals that make mental models. They can learn themselves or from each other, but also on the level of organization, you can create a mental model for all of them that can be learned if they look at that. This is called feed-forward learning, and the way back is called feedback learning in that literature. So that's the picture, the informal picture usually used in that type of literature, and that's what we have to make computation now. You can refine this. By the way, it has efficiency advantages, because if everybody has to learn from everybody, that gives a lot of complexity, and it's easier when you make it a bit more centralized like that. And of course, you can increase your quality by doing so as well. You can also have an intermediate level, so this is also a picture often happens in literature. So this is the part that I wanted to discuss about the mental models and the first steps towards organizational learning. That will be explained now in much more detail by July.
Yes, people have mental models and they learn, and organizations also learn. The development of organizational learning consists of 4 different stages. Individual learning of mental models. This is our first phase in our model also. In this first phase, individuals improve their mental models. In second phase, their shared mental model is formed by individuals. This is the feed-forward learning part of organizational learning. And in the third phase, individuals start to learn from their shared mental model. It's feedback learning from organization to individuals, and it's called instructional learning. And the last one is the improvements of individuals with the help of their shared mental model created in the second phase. One of the reasons that make this topic interesting and worth exploring is that organizational learning both represents learning level and mental situation of people in an organization, and also becomes separate from individuals and even affects them at some point. I mean, for example, we can say that a society, maybe not the whole society, only a part of it, create a culture, but the shared culture becomes very strong and it starts to create the individuals after a point. It's both dependent and independent from people. It's like a chicken and egg situation. Individuals create organization shared mental model and organization creates them. Therefore, it's really important to study organizational learning. And one of the most popular papers in this area is Kim's paper, and this is a quote from that paper. Organizational learning is dependent on individuals improving their mental models. Making those mental models explicit is crucial to developing new shared mental models. This process allows organizational learning to be independent of any specific individual. And because the mental models in individuals' heads are where a vast majority of an organization's knowledge lies. It's very important to study it. This is the overall cognitive architecture for mental models. We can see the 3-layer structure like in the screen. As I explained in the previous slides, these are usage, adaptation, and control of adaptation. When we try to transform this to a self-modeling network, it's the picture to see the equivalent layers. Layers on the left are the representations of the cognitive architecture for mental models, and the ones on the right side represent the layers of self-modeling network. Base level includes a network of the mental model itself. First order self-model level includes adaptation tools like connection weights for the base level network at the bottom. And the second order self-model level includes the control tools like speed and learning factors. We have an illustrative case adapted from the intubation scenario. Here inside the red box, we have a nurse, we have the mental states of the nurse. And we can see that nurse has knowledge on first two tasks, but not the other ones, and takes action for the first two tasks. While the doctor, these are the doctor's mental states, the doctor has knowledge on last two tasks and takes action for them here. These are the notations and explanations of those four tasks in the previous slides. The preparation parts is held by nurse and the execution part is held by doctor. But in our model, we generalize the states, these notations, by naming them like this. These are the task states for person A, these are for person B, and these are for the organization. In our model, the first person A knows about first two connection, but not the last one for task D. Therefore, this D state is a ghost state for A, is a hollow state. And there's no learning here in the beginning. And on the other hand, for person B, this is the hollow state for person B, because person B have knowledge on this last two connection, but not the first one. Therefore, there is no learning in the beginning for this A state. Comparing this with the previous intubation case makes us think that person A is the nurse who does the first preparation parts, and person B is the doctor who executes the operation. A is responsible for starting off the job, and B is responsible for ending it. And here is our generalized organization states for shared mental model that didn't exist in the beginning because we don't have a shared mental model in the beginning. And we also have, as I said, we have 4 different phases. We have 4 different context states. These are the context states. In the first order self-model level, the upper one, this blue one, we have W states for the connections between the base level states. For each connection, we have different W states. They represent the weight of the connections to make them adaptive. For example, for person B, for the connection between A and B, we have this W state. These are for individual W states. These are the individual W states, and these are the organization W states. To make the formation of shared mental model possible, we need connections from individual states, W states to organization W states like this. These connections are needed in become activated in second phase to make the formation of shared mental model possible. After this activation of these links, these W states become activated also, and they affect the connection between the organization states, base level states, and the shared mental model is created. And also we have the opposite links from organization to individuals to make individuals able to learn from their shared mental model. And this is our overall adaptive network model with all levels. Base level, as I just explained, includes the individuals and organizations' mental model states. It's the core of our model. It can be seen as like this. We have W states here. And in the second order self-model level, we have H states to control the speed of learning. We have M states to control the persistence of the learning. And also we have higher order W states here. Because we have W2W connections and we want to make them adaptive, we need higher order W states here to represent the weight of these connections. And also we have speed factors for organizational states. This is our simulation result, the overall simulation result. These are the phases. These are the phases. This first phase includes the improvements of person A and B's individual mental models. Because person A does not have for state D as in the first phase, it remains at 0 until learning from organization is done. We can see here. First 3 states for person A becomes higher, and for last 3 states for person B becomes higher in this first phase because it's the individual learning phase. And in the second phase, this is the second phase, our shared mental model is formed. These are the shared mental model W states. Because shared mental model is formed here, individuals becomes able to learn from their shared mental model. Therefore, their hello ghost states becomes activated here, and they use the advantage of their shared mental model. And also, there's a difference here, as you can see, because our persons are different and their persistence of learning values are also different. Their forgetting levels are also different. Here is A is more forgettable person than B. Therefore, A's lines are decreasing more. And in the last phase, here, in the last phase, as I said, their hello states becomes non-zero. And we have also these context factors. These are needed to determine the context, the case, because our model is context sensitive. It's depend on the context. We have a lot of context states. And also in the second order self-model level, we have aggregation control states, these C states. And also we have H states for speed factor, M states for learning persistence, higher order W states for the W to W connections here, feedback and feed-forward learning. These C states are here to make the aggregation of individual mental models adaptive. The aggregation part takes place with the help of the combination function. Therefore, these C states represent different combination functions. We have 4 different combination functions: logistic sum, scaled maximum, Euclidean, and scaled geometric mean. And we have 3 kinds of connections, these A to B, B to C, and C to D. Therefore, 3 times 4, we have 12 C states in total. And also, as I mentioned, we have context states to determine the choice of the combination function. We have a context state for knowledgeability, for dependency, and for the preference for type of quantity. For example, if the case will be the following, A and B are both experienced, they are dependent on each other, and their preference is additive. If this is the case, the function will be Euclidean, will be selected as Euclidean. When we use zeros and ones to see the things clearly, we got this table. And if this table is carefully examined, we can extract Boolean propositions for these functions, as you can see in the next slides. For example, for C1, for the state C1, representing logistic function, this is the Boolean proposition. It says if A is experienced and B is experienced and they are not dependent on each other, the function will be logistic. when we look at this table, we can see that this is correct. A and B both experienced, they are not dependent, then the function is logistic. The other Boolean propositions for the other functions are there. And to get rid of this negotiation notion, we just created the opposite of these states, these context states. For experienced states, we have beginner states. For dependent states, we have independent states. And for additive preference, we have also multiplicator preference. And this is the final version of our Boolean propositions for functions. And of course, we need connections from these context states to C states, because context states determines the case and affects the C states. The combination function is selected according to the case itself. And required connections, we can see the required connections in this table easily. These are the context states, these are the C states. And for example, again, for logistic function, for C1, we need connection from experienced A, experienced B, and independent AB. We have double plus for preference states, because when we look at the propositions, we can see that we just used them twice. And here, the order is also important. We should keep the order here. These states also need a combination function, and their combination function has a form like this. It's not a complicated function, but because it will take time, I won't explain it right now. But if you want me to explain, you can ask after the presentation. This is our simulation result of our first scenario. In this first scenario, we used Boolean values for context states, as you can see in this next slide. The context states are either 0 or 1. Therefore, our combination function selection has done in the beginning. Here, the purple one and the black one are the C states, and the selected C state is C2, according to the case. The other part is the classical organizational learning. These are the phases. This first phase, individual learning. The second phase is the formation of shared mental model. Here is learning from the shared mental model, and this fourth one, the last phase, is the improvement of individuals. In the second scenario, we just use non-binary values for context states. It was binary in the previous one. Here we have values like 0.9, 0.4, 0.5 or something. And therefore, our combination functions are not 0 or 1. More than one combination function is selected here. And the software takes the average of them. Therefore, the aggregation of the individuals, the formation of the shared mental model is different here from the first one. The learning levels are different because the different combination functions are used here. In this third scenario, we again used binary values for context factors. They are still, again, 0 or 1, but in this time, we changed the context at 400. With the help of step 1 function, we have a context here, we have a case here, but after 400, we changed our context, as you can see here. Therefore, the combination functions are also changed according to the changing context. And our last scenario is again on the changing context scenario, but for this time we use non-binary values for context states. like in this second scenario, we have non-binary context values. Therefore, our combination functions are different and our learning levels are different, but the idea is same. After 400, the context is changed. Therefore, the combination functions are also changed.